Hello everyone, welcome back to online lecture series on fluid mechanics and hydraulic machines. We are continuing our topic, that is hydrostatic forces on surfaces. First of all, we will do a quick revision of our previous topic. So for the fluids at rest, there will not be any relative motion between the adjacent neighboring fluid layers. So in such cases, the velocity gradient will be 0 as velocity remains 0. So there will be absence of viscous forces or shear forces. Now the forces which are present in such steady fluid is due to pressure gradient, due to pressure of fluid normal to the surface, and second is due to gravity, that is self weight. The next is total pressure and center of pressure. The total pressure is defined as the force exerted by a static fluid on a surface either which is plane or curved when the fluid comes in contact with the surfaces, and this always acts normal to the surface. The center of pressure is defined as point of application of total pressure on surface, and we have done this for vertical plane submerged in liquid. So we obtained the formula for total pressure or force and center of pressure in this way, H star. And we also proved it for horizontal plane surface submerged in a liquid. In case of horizontal plane, H star will be equal to H bar. Now we will derive the same two terms for the inclined plane, which is a bit more complicated. So let's begin. So I would suggest you to be patient while I'm drawing this figure because it is slightly difficult. So let's begin. First we will have a free liquid surface over here in this way. And there will be a inclined plane surface here. So this looks better, the inclination with the free surface. And here this inclination is having an angle theta. So here this angle will be theta, so here the actual surface will be like this. So here this is the actual surface, and let's say that here we are having the center of gravity, and here we are having center of pressure, and we will be taking a small strip for this for our analysis. So now here the corresponding point here will be this for COG, and for COP this will be the corresponding point, and here the height of center of gravity will be h bar, and here we will have h star that we need to evaluate. And the force that is being applied here is this, that is dF. This point will be considered as O, and this will be a plane So for COG, this distance will be y bar and this distance will be y star. So what we have done is we have taken this strip having width dy and which is at distance y from O plane. Here we are having area as dA. So here consider arbitrary shaped surface like this which is submerged in a liquid, making an angle of theta with the free surface. Now let's go through the basic nomenclatures here. A is equal to total area of inclined plane then H bar is equal to depth of COG of inclined surface from free surface. Then we will have H star, that is equal to depth of COP, that is center of pressure of inclined surface from free surface. Now theta is equal to angle made by plane of inclined surface with free surface. Now y bar is equal to distance of COG from O and y star is equal to distance of COP from O. Okay, so this is all about the nomenclature that we have already done. Now we will focus on the total pressure analysis. So let's begin. So obviously we will begin with pressure is equal to rho G H dF will be equal to P into area of strip that is this black strip. So this is like P into dA. So now you can say this as rho G H dA. So this is the value of dF. And now the total pressure force F should be equal to integration of dF is equal to integration rho G H PA. So this will be the total pressure force. Now if we get back to the figure, then one thing that we can say over here is, based on the similarity of triangles, we can say H upon Y. This is important thing. H upon Y is equal to H bar upon Y bar is equal to H star upon Y star is equal to sin theta. So you can check it by yourself based on the similarity of triangles. I can give you a hint on this, that you can try in this way. So let's say this to be H star, Y star, then up to some location, let's say this triangle, where it is having H bar and Y bar, and the angle is same. So once you apply sin theta formula, you will be getting this similarity where H and Y are general terms. So let me write them again. H upon Y is equal to H bar upon Y bar is equal to H star upon Y star is equal to sin theta. So what we can do based on this, we can say H is equal to Y sin theta. So now we can modify our main equation, that is this F, total pressure. F is equal to integration rho G Y sin theta into dA. So now we can take the constant terms outside, that is equal to, here, rho G sin theta integration Y into dA. This is the value of So now here, instead of integration y into dE, we can say it is equal to a into y bar. Why? Because y bar here is distance of COG from OO. So here we can simply replace this, and finally we are getting the value of F is equal to rho G sin theta into A into y bar. And if you see here, we are having y bar and sin theta. So in this similarity, we can write down h bar is equal to y bar sin theta. So this and this are correct. Based on these two, we have written this. So finally we can say that F is equal to rho G A H bar. So this is the formula that we are looking for total pressure. Now we will calculate the center of pressure. The next is center of pressure. So here again we will continue with the force on the small strip, that is dF is equal to rho G H into dE. That we have already done here. Now we will calculate moment of force dF. X is O. So this will be equal to dF into Y. So we can say is equal to rho G H into dA into Y. So now we will calculate. This is only for small strips. So now we will be doing sum of moments. Sum of moments of all forces which is equal to integration rho g h dA by. So further continuing on this, we can say it is integration rho g, instead of h we can write down y sin theta into dE into y. So taking the other terms, constant terms outside, so we will have rho g sin theta integration y square dA. Here integration y square dA is equal to moment of inertia of surface about axis OO. So here this will be equal to I0. And we can continue this over here as rho g sin theta into I0. Now we will take moment of force F about OO. So this will be equal to F into y star, and that we are looking for. So now we can equate these two. So F into y star is equal to rho g I0 will be there. So now y star is equal to rho g sin theta upon F. This there is I0 is there. So if you recall, here we are having this term, so instead of y star we can put it is equal to H star divided by sine theta. So here we can put H star divided by sine theta is equal to rho g sine theta divided by f into I0. So now we are left with H star is equal to rho g sine square theta divided by, instead of f we can write down the formula which we have derived, that is rho g a h bar. H bar I0. So this two will get cancelled, and here H star is equal to sine square theta divided by AH bar, and instead of I0 we can write down IG plus A y bar square. So if you recall, this is based on the parallel axis theorem. So now H star is equal to IG sine square theta divided by A H bar plus y bar square sine square theta by H bar. So instead of y bar square sine square theta we can put H bar square. The first term will remain as it is, Ig sine square theta divided by A H bar plus H bar square upon H bar. So finally we are getting the value of center of pressure. H star is equal to H bar plus Ig sine square theta upon A H bar. So that is the formula that we needed to derive. So let's we are done with this theory, and let's copy this part in our main slide. So that is the derivation for this. Now let's move forward with our new theory. Curved surface submerged in liquid. So first we will draw a figure for this and then we will start. So this will be our curved surface, and this entire surface is filled with, let's say, water. And now we will focus on a small area dA, just like our previous theory here. So this will be the area dA, and when we focus on the forces which are being applied, so the force here will be okay, let me correct it. So this will be our small area like this, and we will see the forces which are acting on this. So it will be a normal force like this. Let me use another color like this. Okay, and here this is acting normal to it, so this will be dF, then this angle will be theta, so we will be getting this as a dFy, and this as dFx. So now we are done with this figure, and there is one more thing, that we can draw a triangle here. For the area part, let's avoid this field and keep this black. So here for the area, small area dA, this will be the dA area, and here this angle will be theta. You can check it by yourself. This will be E, G and F. So this will be obviously here dA cos theta, dA sin theta. So now let's begin. So here the curved surface part is from here A to B, let's say. This is the curved part, curved surface AB submerged in a static fluid. So this is the small area dA that we have currently focused. Now let's begin with the pressure. On area dA, so it will be equal to rho G H. So the pressure force will be equal to P into dA, which is equal to rho G H dA. Now this is, you can say this as a dF. So now we can calculate the total force. So total pressure force is equal to F integration rho G H dA. Now there are many strips like this. So if we are near to B, then we will have then the strips are getting changed everywhere like this. And here the force direction will keep on changing. If you see, the normal force will have different direction for each strip. So this integration cannot be done directly, so we will have the Fx component and Fy component everywhere. So the total force F can be written in this way, is equal to square root of F x square plus F y square, and the inclination of this force will be tan phi is equal to Fy upon Fx, and this inclination will be with respect to the horizontal direction. So now dfx, if you see in this figure, dfx will be equal to df sin theta is equal to df sin theta which is equal to rho g h d a sin theta dfy is equal to df cos theta is equal to rho g h dA cos theta. So based on this, the value of Fx force will be equal to rho g will be outside. So first let me write down in this way. Fy, this is not a negative sign. Okay, let me rewrite it. Fy is equal to integration d Fy is equal to rho g integration h dA cos theta. So now we will focus on two different things. First is here, that is dA sin theta. So what is this? This is actually the vertical projection of the small area dA, that is this portion. It is a vertical projection of the small area dA. So the entire term, that is rho g integration h dA sin theta. So here this will be the total pressure force. This will be the total pressure force acting on a surface. This will be equal to on projected area on curved surface. Okay, and now the other part is dA cos theta. So if you see, dA cos theta is horizontal projection. Horizontal projection of area dA. So when we have let's say integration h into dA cos theta, then this is nothing but the total volume. So that integration will give us this total volume over here. Okay, so when we have rho g integration h dA cos theta, then this is nothing but the weight. So here Fy will be the pressure force and Fx will be the weight force. Wait, let me correct it. Fx, here Fx will be the pressure force. So this is the total pressure force on projected area of curved surface. And here let's say this will be the weight of liquid. Supported by curved surface. Up to free surface. So these are the two forces, and this is the end of this theory. So let's copy this. So this is the end of this theory as well as end of this lecture. Thank you for watching this video.